Hello and welcome to part 6 of my NES emulation series, and in this episode we're specifically going to start looking at integrating sound into the emulation. I'm going to continue the code exactly where we left off from the previous episode, so if you've not watched those episodes I recommend that you do so first. But before we get started, it occurred to me that we've not yet integrated sound into any PixelGameEngine applications. I have done a whole series on working with sound in my Code It Yourself synthesizer series, and the PixelGameEngine adopts a very similar approach, but I thought it would be useful first to create a small demonstration app just to show how the PixelGameEngine handles sound. It might be useful for things other than emulation. So let's get started. This is the code base that we've been working with and can be found on the GitHub. It's the NES emulator so far, but you'll notice I've included a lot more mappers. Now I'll talk specifically about additional mappers in a later video of this series, but for now it just gives us a bit more variation in the number of games that we can test. And I'm going to hijack this project temporarily just to build this sound demonstration video. So I'm going to add a new file and I'll call it sounddemo.cpp. And just temporarily, I'm going to remove the NES emulator. This is so we don't have two int mains in our project. The first thing I'm going to do is pull in the demonstration code that comes in the PixelGameEngine header file. This is the one that draws all of the randomly coloured pixels to the screen. I'm going to stop it from doing that. Unlike the console game engine, sound in the PixelGameEngine is facilitated via an extension. We call them PEGX. We've seen these before with 2D and 3D graphics, so I'm just going to include the extension. To activate the sound extension, I'm going to initialize it in onUserCreate, and I'm setting it to 44100, which is the sample rate of the audio system. I want one channel, so it's really only mono. The NES was a mono device. And those of you that have seen my Code It Yourself synthesizer series, you will have seen these before. But these last two parameters tell the system how to package the data to send it to the sound hardware. You can change them to change the performance of the real-time nature of the audio. But I've found that these two settings work very well for most applications. Because the sound PEGX opens a handle to some sound hardware, we need to release that handle when the application is finished. So this is one of those unusual situations where we're going to override the often underused onUserDestroy function of the PixelGameEngine. This is called whenever you close the window or you return false from onUserUpdate. It gives you an opportunity to clean up after yourself, which you should do. The sound extension works in the following way. As is well established on this channel, the PixelGameEngine creates a thread that it uses to call the onUserUpdate function. And this thread sits in a loop, repeatedly running as fast as it can, unless you've got the vsync option enabled when you constructed it. The problem we face is that the speed of this main thread can fluctuate depending upon what the function is doing, and normally we would alleviate this fluctuation by exploiting the f-elapsed time variable that comes with it. However, sound is unforgiving. The human ear is very sensitive to changes in audio and cracks and pops and buzzes, which reminds me actually, as this is a video about audio, I will warn you now, we're going to have all sorts of squeals and scratches and interesting noises and probably inappropriate volumes throughout, so consider yourself warned. Anyway, the point I'm trying to make is we can't just issue sound samples to some audio device, because the rate at which we issue the sound samples won't be consistent. Instead, samples must be generated at the rate the audio device expects. So to handle this, a second thread is maintained in the sound PEGX. And the speed at which this thread operates is largely governed by the sample rate that we specified when we created the instance of the PEGX. This way we can ensure that sound samples are delivered to the audio device hardware appropriately. But to get the samples that we need, the PEGX is going to request from the main thread a sample of sound when it needs it, and the main thread will then return that single sample. In effect, this request is going to interrupt our main thread. Therefore, to use the sound extension, we need to be aware that there are actually multiple threads now in our application. But this allows the sound hardware to run at the speed it needs to run at, and it allows our application to run as fast as possible. Now I'm quite sure there are going to be many more sophisticated and clever ways to handle this interaction between the two threads, but I'm aiming to keep things simple. So I'm going to create a function, and it's a static function called soundout. This is the function that will be called by the sound extension every time it wants a single sample. And it requests what channel it wants that sample to be for. So in a two-channel system, that's the left speaker followed by the right speaker. It also provides some convenient timing functions. Global time is the time since the application started, and time step is effectively 1 over the sample rate that we specified earlier. We need to tell the sound extension the name of this function so it can call it when it needs a new sample. And we'll do that using the setUserSynth function. There's actually several different overridable functions that can exploit different properties of the sound extension. But this function tells the sound extension, hey, we're generating audio samples, so please call this function periodically. Now let's generate some sound. I'm going to keep it simple again and just return a sine wave. So I'm going to take the sine of f global time, that's effectively my x in the time domain. I'm going to multiply that by a frequency, 440 Hz in this case, which I believe is an A. But we need to convert that frequency into an angular velocity. Basically, we're converting it into radians for the sine function, which we achieve by multiplying by 2 times pi. It's all very approximate here. So let's take a look, and let's hope that the volume is sensible. And hopefully in the background you can hear the sine wave playing. I'm really going to regret making a video about audio this way because I'm simultaneously recording my voice and the desktop output, so the two might not mix very well. Generating a static sine wave is all very well and simple, but we know that we're going to want to do something a little bit more interactive and dynamic for our emulation. So let's have a go at implementing a square pulse wave. This is a very simple waveform, and we've seen it before in the Code It Yourself synthesizer series. It's a wave that looks like this in time. There are many ways to generate this waveform, the most obvious one being to simply have a branching condition to say whether it's high or low at the correct time. But when you start adding such discrete components to an oscillator like this, it becomes hard to work with when you're doing things such as changing the frequency or changing the phase or the more advanced things later on. It can also lead to fairly ugly artifacts because the sound hardware isn't capable of these entirely vertical transitions. So I thought it would be interesting to look at creating a square pulse wave using sine waves. After all, we can construct all sounds out of the addition of sine waves. A square pulse wave differs from a regular square wave. In fact, what I've drawn here is a regular square wave. It is low for 50% of its period, and it is high for 50% of its period. A pulse wave allows you to change this ratio, and that's called the duty cycle. So we might have it high for a short period and low for the remainder. Perhaps in this instance, it's high for 10% and low for 90%. This adds texture to the sound. And the synthesizer aficionados out there will understand exactly what I mean, but it's very difficult to describe verbally. You need to hear it in order to understand it. So I think we'll create a function which allows us to specify a square pulse wave of any frequency, amplitude, and duty cycle. Now, lots of memories flashing back here because I love Desmos.com's graphing calculator. It's great for making videos about waveforms, and I use it a lot in the synthesizer series. So here I'm drawing a regular sine wave. And I've added some sliders. Here I can change the frequency of the sine wave. As the frequency increases, the pitch of the note that we hear goes up. Broadly speaking, you'll see that the sine wave is the one that we've just implemented. But what I'm going to do is add together lots of sine waves at frequencies that are integer steps from each other. I'm going to call these harmonics, and I can add more sine waves by changing this slider here. And so as we add more sine waves, we start to form a sawtooth wave. That's very nice. If I add a second sine wave, exactly the same, but change its phase, so I'm going to make it 50% out of phase with the original sine wave. So when the red one is up, the purple one is down. Very, very simple. And again, this sine wave can be influenced by this slider to add more harmonics to it. So I've got two saw waves that are 50% out of phase with each other. To generate a pulse wave, we simply subtract one from the other, which we can see here with the black wave, which is a very nice square wave in a continuous time domain at a 50% duty cycle. It is equally low and equally high. And the quality of this square wave depends on how many harmonics are in our saw waves. As you can see, as we go to a lower count, the square wave becomes rounder. And this also adds interesting flavours to the resulting sound when this waveform is played. Naturally, the more times that we want to add sine waves, the more computation is required. So creating a really accurate square wave like this is actually quite computationally intensive. We're performing these operations, well, almost 100 times in this instance. But interestingly, because we've got two base waveforms that we can have out of phase with each other, we can change the duty cycle of our pulse wave. It does add a little bit of DC offset, but in audio that's not very important. It's only the change that matters. That's what we hear coming out of the speakers. So I'll just disable these background waveforms, and there we can see we've now got a way of calculating in continuous time a pulse wave function. And if I increase the frequency, that behaves too. What's nice about this approach is that we end up with a waveform which is applicable to the real world. There is no vertical lines as part of this waveform. They're very steep gradients, but they're not vertical. Which means in principle, our sound hardware should have no problem replicating this sound. I mean, there are some laws that govern whether it can or cannot, but it does also mean that we can do lots more interesting mathematics to this waveform if we choose to do so. So let's implement this waveform into the PixelGameEngine now and have a listen to it. And I'm going to be very quick and dirty with this. I'm just going to add 3 atomic floats, because I'm going to change the value of these floats in the PixelGameEngine thread, but I need them to get through to the sound generation thread later. As I mentioned before, lots of tidier ways to do this, but this is quick and simple for a video. And I'm also going to add an additional function called sample square wave, and we'll generate our pulse wave samples in this function. The parameters that it takes in are the frequency that we want to listen to and the time. And I'll start by adding 3 variables. A and B represent the sample values for the underlying sine waveforms, and P is going to represent the phase difference between the two. Since we're going to be summing up a whole bunch of sine waves depending on how many harmonics we're interested in, I'll add a for loop. Both sine waves get the same argument. So I'll cache that here in variable C. It's the number of harmonics times the frequency times 2 times pi times t. And as I've just shown in Desmos, the two sine waves are very similar except one is offset by the phase. And I'm also scaling by the number of harmonics. This keeps things within a reasonable envelope. Once all of the sinusoids have been summed, I'm going to return the subtraction between the two as our sample value. I've scaled it a little bit here, simply because I've obviously already pre-implemented this algorithm. I know what it's going to look and sound like, and I want to scale it so I can visualize it on the screen as well as hear it. So now, when the sound engine requests a sample, instead of just returning a sine wave, I'm going to call our square wave function with the correct parameters. Square waves can get quite loud, so I'm going to change the amplitude of this one, which is effectively changing the volume of it. In OnUserUpdate, I want to visualize the waveform on the screen, like we just saw in Desmos. And I'm not even going to talk through the code for this visualization. It is utterly irrelevant for this video. But you can go and have a look at it. I'll make sure I upload this little demonstration file to the GitHub. It's full of magic numbers and constants. That's just to scale it appropriately on the screen. And I'm also going to be sensitive to some user input. So pressing the Q and A keys is going to change the duty cycle. Pressing the D and E keys is going to change the frequency, and pressing the S and W keys is going to change the number of harmonics that we're constructing our waveform out of. And finally, because we've created some static variables, we need to initialize those too. So let's take a look, or have a listen. Well, you can certainly hear what sounds like a traditional square wave in the background. I'm going to reduce the number of harmonics, and eventually it'll begin to sound just like a sine wave, as we had before. In fact, if I press this slowly, we can hear the additional frequencies being added into the sound, so I won't speak, we'll just listen. And as I add more harmonics, it becomes more buzzy and gives us that classic sort of retro sounding loveliness that we all love. I can change the duty cycle with the Q and A keys. change the frequency, but a little quick warning, this is going to sound terrible whilst the frequency is changing, and that's because changing frequency of a playing waveform actually requires a little bit more sophistication regarding what to do with the phase. But for now we'll just leave it as is, because it sounds pretty funky. So here we go. So we've almost doubled the frequency there, higher pitch note, but our continuous function doesn't care. It's quite happy to just calculate what it needs to calculate. And so there we have it, a very quick overview of how to get sound out of the Pixel game engine. Yes, it's a bit loud and I've not mixed the volume levels very well, but functionally it works. But it has introduced something quite interesting, and that is a real-time audio constraint. Audio is real-time. We can't listen to it slightly sped up or slowed down, we just won't accept that. So this is going to start influencing how we control the timing in our emulation, and we'll look at that in some detail later. But for now, let's get started with implementing the APU, the Audio Processing Unit, which is actually part of the CPU on the NES, although I'm considering them as two separate devices in this emulation. The NES can generate sound from 5 different sources. These different sources fundamentally can be considered different types of oscillator. So it has 2 pulse wave channels, that's a coincidence, isn't it? That can generate a pulse square wave with different duty cycles. These 2 channels are typically used for the melody lines and sound effects in games. A 3rd channel is a triangle wave channel. It's not quite the same as a sawtooth wave, and this is used to give you a more bassy-like sound. The next channel is a noise channel. This gives you percussive instrument sounds, or explosions. And finally, there is a sample playing channel. So this plays what is a very simple waveform. For example, it might be somebody saying "well done" or "level complete." Because in this video we've spent some time looking at how to get sound running with the Pixel game engine, and we'll spend most of the rest of this video looking at how we implement sound into our emulation, I'm not going to detail many of these channels. But we'll look at that in part 2 of this audio series. On the hardware, the NES is also capable of specifying the duration of a note, its length, and its frequency. So we can see already we're starting to build up a set of parameters that influence the sound coming out of a channel, and not all of the channels have the same set of parameters either. So for a specific channel, once the waveform is generated, it's associated with a length, which is how long is it played for. And for these pulse wave channels, it can also be swept. Now that means its frequency is changed in real time. If the frequency is fixed, we get a continuous note, like beep. But if the frequency is swept, it automatically increases or decreases the frequency over time to give you a boop or boop kind of sound. Both of these are controlled with dedicated hardware. We also have the ability to enable and disable the channel. These pathways per channel ultimately become summed to give us our final output sample. This final waveform playing channel I'm not going to consider for the time being. And for this video, I'm not even going to consider these additional properties of the pulse wave channel. Now you might be forgiven for thinking this means we're not going to get very far, but you'll see that once we've got the framework in place to start generating sound, adding the other channels is not very complicated. But it is the establishment of this framework which is critical to get right, because it's going to completely turn the emulator upside down. Even though the APU is actually physically part of the CPU, it was a special chip produced especially for the NES, we can treat it as a completely separate item on the bus. That's why we've been able to get away with not implementing it so far and having no negative consequences applied to our emulation. As with the PPU, the APU has addresses mapped into the CPU address bus. It has quite a bunch of them, and the fantastic NESDev wiki lists them all. So we can see we've got our triangle channel, we've got the noise channel, we've got this mysterious sample channel called DMC, but today I'm interested in the pulse channel. And the documentation takes you through the steps I've just outlined, where we've got the length of the note, we've also got the frequency sweeping, and we've a few other things in there too. But for this video I don't want to get stuck into those details necessarily. I've added a class to the codebase called olcPixelGameEngine, which is the designation for the combined CPU and sound hardware, though I'm only going to include sound stuff in it. And because it's a device attached to our CPU bus, it needs all of the CPU bus functions we've become familiar with. We need to be able to write to it, read from it, clock it, and reset it. And I've gone ahead and implemented some blank functions to do this. In the CPU write function, I've included all of the addresses that influence the sound hardware, and the CPU read function and clock and reset functions don't do anything just yet. I'll start by adding very basic functionality and discuss it as we go along. And for now, I'm just going to implement the Pulse 1 channel. And all we know right now is that we can enable this channel, and it's going to output a sample. Now the samples are all going to be double values. They're going to be analog values that are going to be outputted to the PEGX extension. And in fact, because all of these samples get mixed together from the different channels, I'm going to create a function called getOutputSample, which performs that mixing. Since we've only got the one channel, that's a very trivial function indeed. Our new class doesn't do anything yet, but we should add it to the bus. So along with the CPU and PPU devices, I'm going to add in the APU. Don't forget to include it. And this again shows how our bus has transformed from just being a data carrying device to the actual NES system itself, and we'll see at the end of this series that the bus is the NES. Once we've connected the APU to the bus, we need to be able to let the CPU write to it. So I'm going to add in sensitivity to all of the addresses that the APU is interested in, which happens to be this range 4000 to 4013, but also 4015 and 4017. This is a little bit fiddly because in the middle of this range for sound, we've also got the DMA transfer stuff and the controller stuff, so we just need to be picky about what we choose. We can now write to the APU. For now, I'm not going to implement an equivalent read, because it emphasizes that the APU is really a fire and forget device. We just throw data at it and it acts completely independently to everything else that the NES is doing. In the bus's clock function, where we clock the PPU and the CPU, we're also going to clock the APU. And I'm going to clock it with every single bus clock. But we're starting to see a problem. How are we going to get the audio sample out of our NES and into our emulation container? I've strived to keep the NES implementation as encapsulated as possible. I don't want to start breaking into it with threads and event queues and all sorts of interesting architectures to facilitate the connection to the sound extension. And so I'm going to keep this half of the NES very simple. I'm just going to add a simple public variable dAudioSample. So at any point, the emulation can interrogate the instance of the bus and say, well, what is your current audio output? And this is where we start to face a problem that I introduced at the start of this video. The audio system is running in one thread at one speed, and our NES emulation is running in another thread at a different speed. In fact, so far our NES emulation is running at super real time, i.e. we're clocking the NES faster than real time, so it's going to be technically generating audio samples far faster than the system can process them and receive them. We're effectively crossing a time domain boundary, and universally whenever that happens you might want to consider buffering between the two. However, this does add some complication, because what happens if the NES emulation thread fills that buffer? The sound system hasn't emptied it. We're going to start introducing latency in the sound. What happens if the sound system is emptying that buffer faster than the NES is generating audio samples? Well, the buffer becomes starved and we're going to get artifacts and glitches in the sound. So even though we've got to cross this temporal boundary, using a buffer isn't necessarily the best way. Instead, I'm going to take quite a different and radical approach. We know that the sound thread runs in real time, and this is something that we cannot change. We can't change the speed at which we hear the sound. But what we do know is that we can emulate the NES very quickly in this system. So what I'm going to do is every time the sound thread requests a new sample, I'm going to perform enough NES emulation to cover that time period of the sample. Which in effect means that our NES emulation now needs to be controlled by the sound thread. This is called synchronizing to sound. We may see slight variations in the frame rate, but they'll be barely perceivable and quite acceptable to us humans. But it does mean that we'll always be synchronized to our sound. and we don't need to worry about crossing this boundary between the two time domains. And it's for exactly all of these reasons why this video is specifically about changing the architecture of our emulation rather than generating the sounds for the games, although we will get to that in this video. We're currently regulating the speed of our emulation in quite a crude way. We're effectively creating a 60 Hz ticker, and on each tick generating enough NES clocks to create a single frame of output. This has always been approximate, and as I've maintained from episode 1, it's not my intention to create a cycle-perfect, temporally accurate emulation. And so far this has been sufficient for us to try games at a plausible and playable frame rate. The approach here is that instead of regulating to this artificial and rather variable timing system, we're going to rely on a very accurate timing system that comes from our sound hardware. And so in the onUserCreate function, I'm going to initialize the sound extension as we did before. The critical thing here is this number. This is our sample rate for the system, and this will be very robustly reinforced by the operating system and the audio drivers. And just as before, I'm going to add an accompanying soundout function. And we mustn't forget to clean up after ourselves too. Currently, all of the emulation and user input and everything else is occurring in the onUserUpdate function, which is called once per frame of the game thread. Now that we're letting audio control things, we want to call things from the audio thread. So I'm going to encapsulate all of the core emulation functions in a new function called emulatorUpdate with audio. And I'm effectively going to duplicate the contents of the onUserUpdate function, but remove from that anything that interferes with the clocking. Effectively, this function now just draws the state of the emulator. I don't want to lose what I had before because it might be useful for debugging, so I'm going to rename the onUserUpdate function to enable update without audio, just in case we want to go back to how things were. This now means I don't have an onUserUpdate function, but I need one. And all this onUserUpdate function is going to do is call our emulateUpdate with audio function. It's going to effectively just draw the state of the emulator to the screen. This means we're going to clock the emulation from our soundout function. So every time a system audio sample is requested, we're going to perform enough emulation clocks to cover the duration of that sample. And this effectively instills a real-time nature to our emulation. We have a few little multi-threading headaches to sort out first though. I'm going to create a variable called pinstance, and it's of type demo olcNES, which is the name of this class, the derived class from the PixelGameEngine. And in my onUserCreate function, I'm going to set pinstance to this. So this allows me to access a specific instance of the class from a static function. And so in this function, I can now call the NES's clock function, which clocks the bus, which clocks the CPU and the PPU and the APU and everything else. And I can return the audio sample that the bus is currently storing. Even though conceptually this is correct, technically it's actually quite wrong. We know that our sound system is going to be running at approximately 44 kHz, but we know that our NES clock is running in the range of megahertz. Therefore, we must execute a number of NES clocks equivalent to one sound sample duration. So how do we calculate that? To the NES bus header, I'm going to add another function called setSampleFrequency. And this function will be used to inform the APU about the temporal properties of the surrounding emulation system. I'll add in a private variable called dAudioTimePerSystemSample. So this is the real-time duration between samples required by the sound hardware. And to accompany that value, I'm also going to add dAudioTimePerNESClock. So this is the real-time duration that elapses during a real-time NES clock. Now we're emulating faster than real-time, so this will be a constant that describes how much artificial real-time passes per NES clock. Let's add the body of this function to the bus class. The audio time per system sample is simply 1 over the frequency. Now I'm clocking my APU at the same rate I'm clocking the PPU, so the APU is going to receive a clock every whatever that is in emulation time. And this is a number derived from the core crystal frequency used by the NTSC NES.
And it's interesting that one of the things I discovered whilst working on the APU is just how many magic numbers are going to be involved. That's just how it is in this case. Clock frequencies need to be fixed to suit televisual broadcast standards across the world, and things like note frequencies and durations are also fixed, so we'll see quite a lot of hard-coded information in the APU implementation.
Now we have two durations which we can compare in such a way that we can determine whether our emulation is behind real time or in front of real time, and we can use this comparison to output a sample at the correct time to make sure that we are synchronized with our audio. On the bus, I've changed the clock function from a void to a bool, and it's going to return true if that particular clock cycle yielded a new audio sample in real time. This way we can repeatedly clock until this function returns true, because we're clocking from our sound thread, and the sound thread is requesting a single sample. I'll add an additional variable to our bus, which is just going to accumulate the elapsed audio time in between system samples. And now back in the bus's clock function, we can start synchronizing with audio. I'll start by creating a small bool, and it's this bool that will return from our clock function if there is an audio sample ready. Every time this clock function is called, I'm going to increment the dAudioTime variable by our dAudioTime per NES clock. So even though the clocks might not necessarily be called in real time, we can create an accumulation of how much real time has elapsed. If we know that that accumulation of real time is greater than actual real time, the time per system sample, then we've got an audio sample ready to be delivered to the audio system. So I can reset my dAudioTime accumulator, get the current valid sample from the APU, and set my sample ready flag to true. Going back to the main emulation source in our sound out function, now it becomes obvious that I want to sit repeatedly clocking until this function returns true. Because then, and only then, is there a sample ready in real audio time to send to the sound hardware.
Doing things this way has removed our ability to step through the code line by line, or step through frames frame by frame. I'm okay with that for now. We'll bring that back in as we complete the emulator. But what we can be sure of now is that our emulation is going to be running in real time, and that our audio hasn't had to cross any troublesome temporal boundaries. Now, those of you thinking ahead might be thinking this is a really inefficient way to do things. Why would we be clocking the NES per sound sample? Surely that means our sound out function is going to be called 44,000 times per second. That's a lot of overhead. How's it going to handle it all? Well, that's not quite true. Even though the Pixel Game Engine presents this function as requesting a single sample at a time, that sample isn't requested in real audio time. The sound hardware actually requests a block of 512 samples at a time, and you see those successively being called by this function. So we're always actually emulating faster than real time, we're emulating the audio faster than real time, but the audio system won't allow us to progress until all of the samples have been played and we're back in sync. I know it's a little bit complicated, but it's sound. Sound stuff is always a bit more complicated than graphics.
In the onUserCreate function, once we've created our NES object, we need to tell it what the system's sample frequency is. This way it can go away and calculate the constants it needs to. And it also allows a little bit of flexibility if your system isn't running at 44.1 kHz. It could be running at 48 if it's particularly high end. Now, even though we're not generating any audio yet, it's probably worth running the emulator to see if our timing is reasonably accurate. I'm going to click run here, and it's Super Mario Brothers, and we can see that it is running, and to my eyes it looks like it's running at the right speed. We can try having a play of the game. But this timing is now completely governed by the sound system. In fact, it plays just fine. Doesn't necessarily mean I'm playing just fine, but you know what I mean. Now, because we put that constant in of the NES's clock speed, and we've developed a relationship between the NES's clock speed and the speed that the sound hardware is moving by, we've actually got this quite accurate speed for the NES now. Which is interesting to think, that something as simple as sound is going to be so responsible for how the emulator behaves.
So now it's time to get noisy.
At the heart of each NES audio channel lies something called a sequencer. And fundamentally, a sequencer is just a counter that counts down. And it only counts down if the sequencer is enabled and it is clocked. If the counter becomes 0, then we do something. And then we reset our counter to some known value. What the sequencer actually does is different per channel. But what we can see here is how the sequencer is controlled. We can change the rate at which it is clocked. That will increase the rate at which the counter is counting down, and that will increase the rate at which something is done. We can also increase the rate at which something is done by changing the reload value. If it's counting down from a large value, that's going to take more time than counting down from a smaller value. And we can also stop it doing anything at all. So let's assume I have an 8-bit word that looks like this. And we could consider this word to be a 50% duty cycle square wave. It's low and then it goes high. We could configure our do something function to rotate this word, for example. So on the next do something, it's 0, 0, 0, 1, 1, 1, 1, 0. And again, if we always output a specific bit each time there is a do something, over time what we'll see is a square waveform. If we increase the rate at which we clock, or decrease our counter value's starting point, we effectively change the period between the do something functions. In effect, we have changed the frequency of this square wave output. And therefore, with this very simple approach, we can generate different duty cycle pulse waves at different frequencies. For example, here it's a 50% duty cycle, but it could be 1/8, which would just be 0, 0, 0, 0, 0, 0, 0, 1. And the same method is applied, but we only see a pulse periodically, and the frequency of which that pulse is outputted depends on this reload and our clock values. And as we saw at the start of this video, as we increase the frequency of these waveforms, effectively we hear a change in pitch. The pitch gets higher. And so the sequencer for the pulse wave channel really does two things at once. It sets the frequency of the output waveform and it sets the duty cycle of it. To the APU header file, I'm going to create a new struct called sequencer. And in here we can see we've got our counter value called timer, our reload value, which is what our counter gets reset to. We've got an output, which is an instantaneous output for the sequencer, and we've got a variable called sequence, which represents just some data stored in the sequencer. In this instance, it could be the 8-bit waveform, but we'll see for other channels that this can change. And because the sequencer can change, the do something nature of it, I want to remain fairly flexible. So I'm going to add a method to this structure called clock, which takes in an enable flag, and it also takes in a function pointer to a small lambda function which implements the do something part of this structure. Each time this structure is clocked, if it's enabled, we decrease our counter by 1. According to the NES spec, this particular implementation is sensitive to when the counter effectively reaches -1, it does its thing. So that's what we'll be sensitive to if timer is equal to 4fs. If that is true, then we'll reset our counter value to our reload value, and we'll set the output of the sequencer to be the least significant bit of our sequence data. In all cases, every time it's clocked, we'll return this output value. Just for convenience. It's there anyway publicly as a member of the struct, but you never know, using it in line could be convenient. So all that's left is to add the do something part of this structure, and that's passed in as a small lambda function. So this lambda function is going to be provided somewhere else, and it's going to operate on the sequence variable contained within the sequencer struct. And to accompany my pulse1 enable and pulse1 sample variables, I'm going to add an instance of the sequencer called pulse1 sequence. Time to add some body to the clock function of the APU. The clock for the APU runs at half the rate of the CPU clock, and the CPU clock ran at 1/3 of the rate of the PPU clock, i.e. the PPU clock is 6 times faster than the APU clock. So I'm going to maintain a clock counter variable because this is called every PPU clock, and when this clock counter variable is evenly divisible by 6, then we're going to change the state of the APU. At the moment this method is fine, but what we'll see later on is actually we do need to be sensitive to clocks at higher frequencies than just this. This means to the header file I need to add 2 working variables for the APU, and these are going to be clock counter, which we've just discussed, and also frame clock counter. And this is quite an important concept because it's the frame clock counter which is used in maintaining the musical timing of the APU. So for every valid clock counter for the APU, I'm going to increment my frame clock counter. And depending on the value of the frame clock counter, I'm going to set 2 flags. One happens every quarter of a frame and one happens every half of a frame. And again, these are some magic numbers, they just are what they are, but they're responsible for giving you even timing over the duration of one of the NES's internal sample periods. And so they're just set explicitly. This is in 4-step sequence mode. The NES has 2 sequence modes, one is 4-step and one is 5-step, and these loosely correspond to the feel of the music that you're listening to. We'll not get around to really implementing much of that in this video, but I will leave some placeholder code here for you guys to fill in, or I'll fill in the next video. So every quarter frame we're going to look at adjusting the volume envelope of the output of the chip. And every half frame we look at changing the duration of the notes and the frequency sweepers that we talked about at the start of this video. So frame clock counter is really responsible for maintaining the musicality of what's going on. It makes sure that things are all musically sensible. But as mentioned, for this video I'm just interested in outputting any sound at all at this point. And so I'm going to update here the sequencer for our Pulse 1 channel. Now don't forget this required that we pass to it a lambda function. So the second argument of this is indeed a lambda function, which allows us to customize the functionality for this particular sequencer. The S argument passed into the lambda function is the sequence value stored in the sequencer struct. And all I want to do for this particular sequencer is rotate the word as I showed on the slides before. And there isn't a convenient C++ syntax for doing rotation, so you have to do it manually with some bitwise operations. But effectively what we're doing is taking the upper 7 bits of the word and shifting them right 1, and taking the previous least significant bit and setting it in the most significant bit location. In principle, we know that this will generate for us a square wave waveform. So I'm going to set the output of our sequencer directly to our Pulse 1 sample. So now the clock function does something, admittedly not very much, but it is clocking our sequencer to start outputting a waveform. We now need to couple in the CPU write function in order to characterize what that waveform should look like. Writing to address 4000 on the CPU's address bus is responsible for setting the duty cycle of channel 1's pulse waveform. And so I'll use a little switch case statement to do that. And here we can see I'm setting the sequence of our sequencer depending on a specific duty cycle value. Here we've got 1/8, a quarter, 50% and 3/4. And it's these patterns that will be rotated by the sequencer to produce output. The frequency at which these are rotated is set by controlling the Pulse 1 sequencer reload value, and that happens at address 4002 and 4003 because this timer value is 16 bits and we can only communicate 8 bits at a time via the CPU. The whole channel can be enabled and disabled when the CPU writes to address 4015. So before we give this a try, a quick little recap. We've got a single pulse channel which we have no control of other than controlling its frequency and its duty cycle, and we can turn it on or off. Every time the APU is clocked, we also go on to clock the sequencer, so it's going to be outputting this binary waveform. So let's take a listen. Well, lots of noise. I mean, it's recognisably DuckTales, I think. It sounds...
Well, let's be honest. It sounds really awful.
That's enough of that. Maybe it was a one-off. Let's try a different game. again, it's very recognisable as being correct. If I press start, let's actually go into the game. It never stops producing audio because we don't really enable or disable the signal. So the music is almost right. Oh, that's Mario's jump sound is playing, so I kind of feel as if things are in the right track. It just sounds absolutely terrible. Okay. I think what might be useful to do is have a look at what the waveform actually looks like. So I'm going to use Audacity here just to record the sound being output by the emulator, and we can have a look at it. So I'll press record here and click play. Here is the recorded waveform, and I'm going to zoom in a little bit on it. And we can see it is, well, it's a brutal square pulse wave. In fact, it's too clinical. We can see that some of the pulses are slightly different durations. This could be well due to timing errors in how I've sequenced things. But this is a very demanding thing for a sound system to be able to play. Let's have a look what's going on here. So lots of very high frequencies, starts and stops. This does give a kind of popping sound on the speakers.
We've also not implemented many of the other features, such as note duration, volume envelopes and frequency sweeping, but still I don't think it should sound that bad. So what I'm going to do now is replace this raw sequenced output with the pulse wave generator we created at the start of the video. Isn't it amazing how these things all come together?
To the APU header file, I've created a second struct called oscillator pulse, which contains exactly the code I had at the start, where we're using harmonics of sine waves to create a pulse wave with a varying duty cycle. The NES Dev Wiki actually gives us a translation function to turn the requested value of that particular channel into the output frequency that we want to listen to, given the clock structures for the emulation platform we're targeting, in which case is NTSC for me. So I'm just going to directly implement this function to give me the frequency that I need to pass to my oscillator. Where we were generating the sequence before, I'm just going to comment that out. And instead of looking at the output of the sequencer, I'm going to calculate the frequency I need for the oscillator and sample my oscillator, giving it a specific global time. Conveniently, the global time variable is in emulation time, so I just need to accumulate that. And in this instance, we know that this function will update the oscillator every third PPU clock cycle. And because we've got 1 over frequency equals time, then we have actually got a third divided by the PPU frequency. And so finally, to get my oscillator to work, I need to include an additional variable, global time, in the APU header file. So this time, rather than looking at the binary output of the sequencer, we're going to generate the sound we require. So let's take a listen. Well, it's not much of an improvement. I can't hear anything at all. What have I forgotten? Ah yes, we've not included the duty cycle as part of the oscillator. So up here we were specifying the duty cycle as a sequence. But now we can specify it explicitly. Let's try again. Well, it sounds very slow. And doesn't sound quite right at all. What's still going wrong? Well, the truth is, our oscillator is very computationally intensive. It's slowing down our ability to emulate in real time. And it's because I've got a whole bunch of sine functions. Fortunately, I know a YouTuber that created a video on how to create a fast approximation to sine, which is perfectly usable in audio synthesis. And so I'm just going to copy that directly in and change these sines to use my approximation. Now let's have a listen. And that sounds really, really nice. Let's just try recording that waveform too. And we'll take a look. Random location. And what we see is a far more organic looking waveform. It's not a perfect pulse wave, but it's certainly more amenable to being played on speakers. Let's try a few different games, see what they sound like. So don't forget, there's nothing enabling or disabling the sound, so it will always keep playing. Let's just have a quick try of this one. Oh yeah, you need to press the start key, don't you, before you get anywhere. Okay. Well, that doesn't seem too bad. It sounds strange without having the frequency sweeps when Mario jumps. Oh. Nonetheless, seems to work very nicely. Gotta stop jumping though. But if I stop jumping, I'm gonna get killed. Oh, I'm gonna get killed anyway. Since we've got the additional mappers, we can try these slightly more advanced games now. Let's have a listen to Zelda. Oh no, that's very nice. It's got the vibrato built into it, so you might think they would use the frequency sweepers to do that, but they're not. They're hard coding the note changes. Very nice. It's quite strange just listening to one channel. Let's give it something of a challenge. So this is a terrible game, but it's well known for having one of the best soundtracks on the NES. Well, that sounds cool already. Let's start the level. Lots of stuff going on there. I'll pause it so we can listen to the music. I don't want to play this rubbish. But of course, it's still just the one channel. However, if you wanted to implement Pulse Wave 2, that would be very trivial indeed now, because it is almost a complete clone of Pulse Wave 1. Very simple game, very simple soundtrack, but nonetheless poignant. All sorts of stuff going on there.
And so there you have it, or there you hear it even. We've implemented very basic sounds for the NES emulator, but we've had to do quite a bit to get there. We had to look at how do we implement the sound extension for the Pixel Game Engine, how do we completely reorganize the timing for the NES emulation, and ultimately it turns out that the actual output that the NES would normally give doesn't sound too good on a normal computing system. Now that could easily be because my timing is all over the place and I'm missing half of the features required, but synthesizing our own oscillators seems to be the way forward. As always, this code will be available on the GitHub, and I'll also upload the new mappers as well, which means if you've got some games kicking around, you might be able to start playing them. If you've enjoyed this video, come and have a chat on the Discord. Give me a big thumbs up please, have a think about subscribing, and I'll see you next time for part 2 of the APU, where we'll look at implementing the other channels and having a full suite of instruments to listen to all of that NES loveliness. Take care.